Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be going over SN2 reactions. Now before we start, let's define a few things. A nucleophile is a species that donates a pair of electrons. An electrophile is a species that accepts pairs of electrons. A leaving group is an atom or molecule that leaves another molecule during a reaction. And lastly, a substrate is a compound that's being attacked by the nucleophile. Now this right here is a general, what a general SN2 reaction looks like. You have a nucleophile, which is this right here. And then we have, it attacks the backside, and I won't emphasize on that because it'll come into play a little bit later. It attacks the backside of the electrophile, which is this right here. Specifically the carbon atom, because the bromine atom is pulling electron density away from the carbon. Now, when the hydroxide ion is attacking the electrophilic carbon, it donates its pairs of electrons to form a new bond to the carbon. Now this bold green arrow right here, it depicts the movement of lone pairs on the nucleophile that bond to the carbon atom. Now at the same time the hydroxide is donating its electrons, the carbon-bromine bond must break. So as you can see it right here, the electrons are moving, and the bromide ion is acting as a leaving group. Now we call this whole thing a concerted reaction, meaning that it all occurs in one step, the bond breaking and the bond forming. Now this right here in this little bracket is the transition state, and again this is where the bond of the nucleophile, in this case the hydroxide, is partially formed, and the bond with the leaving group, which is the bromine, is partially broken. Now, the smaller green arrow, as right here, just shows that the electrons from the bond between the carbon atom and the bromine are essentially breaking to form that leaving group by itself right here. Now, if we look at this right here, we can kind of remember the SN2 reaction like a great rear-ended car crash. When the yellow car rear ends and hits the blue car from the backside, a leaving group, and in this case would be the person flying out of the car, and the product is that you have two smashed cars plus a leaving group and a person that's injured. So now there are four factors that affect the SN2 reactions: strength of a nucleophile, steric effects of an electrophile, solvent, and a leaving group. So let's dive into these a little bit more. So the strength of a nucleophile, negatively charged species is favored over a neutral charge. For example, a base is stronger than its conjugate acid at being a better nucleophile. So we can look at the example of hydroxide versus H2O, water. Now hydroxide is a better nucleophile than water because it has an extra pair of electrons that can be donated to the electrophile, and it also contains a negative charge. Now in terms of like the periodic trends, with rows, the more nucleophilic, it gets more nucleophilic as you go left, and with the columns, more nucleophilic as you go down. For the rows, the more electronegative ones have their electrons held tighter and they're not as likely to form the bonds. As with the columns, as you go down, it increases its size and it makes it more polarizable. The next effect is the steric effects of the electrophile. So an electrophile, like we said before, is also known as a substrate. And so the nucleophile must be able to get to attack the substrate from the backside. However, as the substrate gets more crowded in terms of alkyl groups, it gets harder for the nucleophile to attack. So we call this prevention of interactions steric hindrance. And right here is a primary substrate, which means that it only has one alkyl group indicated by the R. And that will react with the nucleophile faster than a secondary nucleophile, or I'm sorry, a secondary substrate, which will then have less crowdedness, and then so on and so on. So this right here is also a tertiary substrate because there's three alkyl groups attached to it. The next is the solvents, and so these compounds must be dissolved in something, and so this is where the solvents come into play. Polar aprotic solvents favor SN2. So a protic solvent doesn't have an acidic proton, whereas a protic solvent does have a acidic proton. So these solvents, the aprotic solvents, usually don't have a hydroxyl or an amine group because those groups contain the acidic protons. Now with an aprotic solvent, the nucleophile isn't as heavily solvated as it would with a protic solvent. So you can think of it as a concept of hindrance like we mentioned earlier. Less hindrance in this case would be the less protic solvent, the better for the reaction, and the nucleophiles more freely available to react. So right here is a list of some of the aprotic solvents, and again this is not an all extensive list, but be sure to check out your textbook for more aprotic solvents. So what we have here is DMF, dimethyl formide, acetone, DMSO, and DME. Now the fourth and final factor is the leaving group. And so weak bases want to accept electrons and are thus good leaving groups. And weak bases, again just a reminder, are conjugate bases of strong acids. So examples of strong acids are hydrochloric acid, hydrobromic acid, and hydroiodic acid. Now their conjugate bases are Cl-, Br-, and I-, which are weak bases and thus serve as good leaving groups. Another example of weak bases that are good leaving groups are sulfonates, sulfate groups, and phosphate groups. Now the reason why these are really good leaving groups is because they're able to form resonance structures that help stabilize the molecule. Now lastly, you can have something like an alcohol group which becomes a good leaving group. However, that's a very particular case because the alcohol has to be put in some type of acidic solution, which then allows the alcohol to be protonated by the strong acid, and they can be converted to a better leaving group. So that's just a small portion of it. Now the last part I want to talk about is the stereochemistry. So we can see right here again that if we go to this particular diagram, we mentioned that the nucleophile attacks the opposite side of the leaving group. So again, just for a reminder, this is the nucleophile and this is the leaving group. Now doing so with that backside attack causes an inversion of configuration at this carbon. So if you notice that the hydrogen atoms bonded to the carbon, on the left you have this dotted line bond, which means that it's coming into the page, and then you have the wedged one right here, which means that it's coming out of the page. So this comes first, I guess if you're reading from left to right, left first and second, and then right when it attacks, you can see that these two shift as the wedged one comes first and then the dashed or dotted bond comes second. So what we say is that we call that is a inversion of configuration. Now this is important because the stereochemistry is different from the SN1, which we'll go over in the next video. So this right here is just a summary sheet of the SN2 reactions. Again, the nucleophile attacks the backside of the electrophile, the transition state forms, and the leaving group leaves and forms product. The four factors that affect the SN2 reactions: the strength of a nucleophile, steric effects of an electrophile, solvents, and leaving groups. And again, on the bottom, this is just a general schematic of what an SN2 reaction looks like. Now that concludes our SN2 video today. Hit that like button, subscribe button, support the channel, and share it with your friends. In the next video, we'll be going over SN1 reactions, and let me know down below what videos you'd like to see next. Social media links will be down below, and just remember, you gotta yo.